curve is g of x. Well, we want to know not from the x-axis to the curve, but from 4 down to the curve. So we're going to do 4 minus g of x.
And we can just write g of x.
Yes, you can just write g of x. Then the inner radius is from the axis of rotation to the edge of the area that's closest to the axis. So what would that be? 4 minus f of x. And that's all you have to do on this. It's just set up. And it's worth 3 points. Yeah. Key is just knowing outer radius, inner radius. So, oh wait, oh, this is the wrong problem. I was like, oh my god, that's not the right thing. That's the other problem that we did. Oh, I don't think I pulled it up yet. 2013 scoring guideline. I was like, oh no, we did the wrong thing. Okay, part B, 3 points. 2 points for the integrand, which is, and they're showing you both of these in case instead of writing f and g, you actually wrote out the equations. You don't have to do that. These are both the correct answers. Oh.
Is the bottom line.
Oh yeah, that's right. Yeah, f of x is the bottom line.
Oh. Oh, okay. Yeah, I was about to say, what? We did it wrong. Sorry, yeah. I just couldn't read my own label. Oh my graph, yeah. F of x is the parabola. It's on the bottom. Yeah. Okay. Yeah. Sorry, that was my fault. Yeah. So f of x is the bottom, and g of x is the top. So you would get the 1 point for the limits and the constant, which the constant's the pi. That's what I was talking about. If you get the limits wrong or you forget the pi, you would not get that 1 point.
How did we get the limit?
That's the x coordinates for the two. Let me pull up this again. That is where they intersect, right? So they start intersecting at 0, and then it goes to 2, right? So these are x coordinates that the volume is between, right? It's between 0 and 2.
And if we had a calculator, we could plug that in, right?
If we had a calculator, yeah, we could just plug it in to find it, yeah. All right, and then on part C says the region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Write, but do not evaluate, an integral expression that gives a volume of solid. So this is like the one we did on the 2015 test. So we have this area, and there's squares riding up out of the area. And it creates this 3-dimensional solid, right? So it's like, I don't know, something like that. Right, but the key is you just have to know how to find the area of one of those cross sections. And the area of a square is just side squared. So we just have to figure out how long a side of a square is. Right? And again, it's just top curve minus bottom curve. So when you want to find the volume of a solid with known cross sections, so this is not washers, you're not rotating. This is squares. We're finding the area of each square and integrating that. So we're going to integrate from 0 to 2 the area of the square, which is side squared. Right. And this each side of those squares is top curve minus bottom curve. The distance between those two curves. So it's just like with washer integrating the area of a circle. You're doing pi r squared because your cross sections are circles. They're washers. Here your cross sections are squares. So you integrate the area of a square, which is side squared. Now you gotta just set it up. And that's worth 2 points. So 1 point for g, knowing that it's g minus f squared, and 1 point for the limits. And there's not a constant. I don't know what they're talking about there. Let's see. Each cross section perpendicular to the x-axis of the square. So they're telling you to draw the cross section perpendicular to the x-axis and make them in the shape of a square. So perpendicular to the x-axis means that they would go like this, right? They would make right angle with the x-axis, and so that's going to be the side of the square. That's the distance from the curve. Yeah, from the top curve to the bottom curve. So think so. Okay, so let's look at, I learn a little bit better about these. A little bit, yeah. All right, let's look at 2012. 2012 was back on the calculator portion, number 2. And parts B and C again were the whole right but do not solve kind of questions. Alright, so number 2 says let R be the region in the first quadrant bounded by the x-axis and the graph of y equals ln x, which would have to be this one, because the other one is a line. But you can use your calculator to figure that anyway, so it's a calculator problem. And y equals 5 minus x, so that would be this other one. The straight line. Find the area of R. Alright, so to find the area of R, we're really going to have to break this into 2 areas because our 2 graphs don't really overlap. This isn't like finding the area between 2 curves. This is finding the area between a curve and the x-axis. So this is just basic integration. But we do need to split this up because we do have 2 different equations involved. Right. So we need to figure out where they intersect because that's going to give us this value right here. And then we're going to integrate from 1 to that value to find this area. And we'll use this equation. And then we're going to integrate from that value to 2, 3, 4, 5. And use this equation to find this area. And then we'll add them together. So the first area, let's see, we're going to integrate from 1 to, let's figure that out. I'll go to my graph. And type in the natural log of x and 5 minus x. Now I'm going to change my window. The window on my paper looks like it goes from about 0 to 2 on the y and about 0 to 5. So I may go into like 6 just to make sure I can see all the graphs. So menu, window settings, 0, 6, and 0, 2. I might make my y go a little bit bigger. Okay, there we go. You see a little bit better. It doesn't really matter if you see it just like on the paper. The main thing that we need the graph for is just to find that point of intersection. So as long as you can see that point of intersection, the window doesn't really matter. So we're going to analyze the graph to find where they intersect. It's down, you see it, it's in blue. But I think you can also just type L in parentheses X, yeah. And I'm going to save the X coordinate since it's not just a nice number like 0 or 2.3. I'm going to save it since I have to use it to find an answer here in a minute. So remember, just hover over until it turns kind of light gray and then press Control menu. If you press Control menu on attributes, you can hit show more decimal points or less on that very first one. So I'm going to store it. Control menu. I'll store it as, I don't know. I'll store it as J. Some of you know what you store it as. So I'm going to write on my paper. J is 3.693. J, which is 6.9. Is that what y'all got for the point of intersection? Oh, okay, so I just want to make sure I didn't make another mistake. So press menu and then analyze graph and number 4 and find the point of intersection. Okay, so we're going to do from 1 to 3.693 of ln x. Alright, because that's the curve that makes that first part of the area. And then we'll add from j to 5 of 5 minus x. So that's the curve, then that second area. It's just the area between the curve and the x-axis. So that's just a standard, that's what a normal integral does. It tells you the area between the curve and the x-axis. It's only when you go between 2 curves that you have to subtract. So this is the area of the first half of R. This is the area of the second half. I type that in. And I have ln x in my f1, so I'm just going to put f1 of x dx plus j to 5, f 2 of x, yeah, 2.986. That's what we did. 2012 over 2. So this is 3 points. They showed 2 different ways to do it. I never would have thought to do it the other way that they did. Okay, so here is, this where's 3 points. It's 1 point for the integrand, so knowing that you need to integrate natural log of x and 5 minus x. 1 point for getting the 1 to 3 point, whatever it was. Wait, is that the one? Yeah, okay. And then 1 point for the answer. They did it another way where they did everything in terms of y, but I wouldn't do that. It's actually, to me, I wouldn't even think to do it that way. So it says 4. You can do it either way. That's 3 points. Each part on this one is 3 points. 3, 3, and 3. And to me, that's the hardest part of this one, because the other 2 parts I get just set up. Okay, so then on part B, region R is the base of a solid. Really, what's that? Alright, so part B, region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Write but do not evaluate an expression involving one or more integrals that gives the volume of the solid. Right? So this one is a little bit different just because we did have to split this up into 2 different sections because there's a different curve making these 2 areas. But the nice thing is that both of them touch the x-axis, so we're really having to work with one curve at a time. We have to work with them separately. So to find the volume using squares, we're going to integrate the area of a square. Now we're actually going to have to do this twice because the squares in this first section are going to have different side lengths than the squares in this second section, because these lengths are different, are founded in a different way than these lengths, because we're using 2 different curves to make those lengths. So we're going to actually have to do 2 squares here. Right, so this is area of a square, which is 5 squares. And you don't have to label it like this, I'm just labeling it like this so that you'll remember what we were doing. Right. So the first one's going from 1 to my j value. The second one's going from j to 5. So what's the side length of each square in the first section? What is this distance here from the x-axis to that curve? Oh, sorry. What is this distance here? Just ln x, right? It's just ln x. And then this distance here, just 5 minus x. Right? So that's all I have to do on that one, is just set it up. Right? In the first part of it, the squares all have sides of ln x squared, and then in the second part, the sides are all 5 minus x squared. So you just have to set that up. And that's 3 points. Let's see what the points are for. Okay, yeah. So 2 points for the integrand, so ln x and 5 minus x squared, and then 1 point for the expression for the total volume, so adding them together.
It's just a line because the x is on the bottom.
Yes, yeah.
So
Now if it had been like something else, like if they'd put it, like said it was, you know,
-2 or something.
right, we would have had to add 2,
Okay.
Yeah, because remember, y always measures from the x-axis. So as long as you're measuring from the x-axis, then you can just use your function. It's only when we measure from somewhere else that we have to worry about adding or subtracting or whatever. Right? And then part C says the horizontal line y equals k. Ooh, a horizontal line. Ooh, this is going to be interesting. Alright, so the horizontal line y equals k. So now we're dealing with a horizontal line. When it starts doing things horizontally instead of perpendicular to the axis, everything has to be changed to be in terms of x. So maybe this one is a little bit harder than I originally thought. Alright, so this is y equals k. And it's going to divide it so that these 2 regions have the same area.
The top and the bottom?
Yeah, so the